Coming up on Warplane, surveillance has always been a crucial component of aviation.
The aircraft was used clandestinely for photography.
But as defenses improved, spy planes had to fly higher and faster. With avionics and stealth, the warplane became almost invisible, and pilots a liability.
Human performance is clearly the limiting factor in a modern high-performance aircraft.
Conflict drives technology on Warplane.
This is the very latest fighter in the United States Air Force, the F-22 Raptor. With twin jets that deliver up to 35,000 pounds of thrust each, the Raptor can fly efficiently beyond the speed of sound for extended periods, a capability known as supercruise. The F-22 can strike and be gone in seconds. Not only is it fast, the Raptor is almost invisible to radar. It is a stealthy machine. The pilots who fly the Raptor must be at the peak of their profession. It takes almost as long to train them as it does to build their jet. But the 100-year relationship between pilot and plane could soon be changing dramatically. The Raptor is designed to fly, think, and if necessary, attack without human intervention. Where the warplane is going, man may no longer be able to follow. By the middle of the 20th century, jet and rocket engines had made global warfare an authentic threat. During the Cold War, both sides scrambled to develop early warning systems against the ever-growing threat of long-range aerial attacks. Today, aircraft like the AWAC are at the heart of the early warning system. They patrol the battle space and act as communications hubs. Powerful onboard computers and their operators interpret the information. They can identify friend or foe and direct an immediate response. The AWACS are at the forefront of technology, but the origins of their mission are as old as the warplane itself. As far back as the First World War, airplanes proved their worth to military commanders by becoming the eyes in the sky. They flew reconnaissance over the battlefields, detailing troop movements, photographing enemy trenches, and providing crucial maps for the forces at the front.
If you go back to World War I, both sides do a lot of aerial photography. In fact, a lot of the air fighting in World War I is to prevent people from taking those photos.
The effectiveness of aerial photography made the reconnaissance plane a lethal weapon, one that had to be shot down. It didn't take long for countermeasures to develop. But the photographs were essential to the ground troops, and both sides demanded them at all costs.
Just about see.
This is a German camera from World War I, and it's the early years. It is a plate camera, has a plate back on it. The body on the camera is largely wooden. It has an extremely simple sight, and you would have been using this leaning over the side of a cockpit in an open aircraft, probably at 7,000 or 8,000 feet over the front or lower, but difficult to use.
The cameras were not easy to manipulate in such conditions, but the results were worth the challenge and risk.
This is a World War I photograph, and I think at that time you can say that with the height limitations and with the target, and you were looking very much at the front line here, you were looking at something where the quality was adequate for the need. What the intelligence officer in those days was looking for was the structure of enemy trenches, the positions of barbed wire, Trenches were very obvious, beautifully castellated, and particularly with the Germans, very good soil disposal, so trenches stood out very well. We can trace the barbed wire on this photograph extremely well, and this is because the weeds and the grass under barbed wire are uncontrolled, and you do get quite a dark shadow from growth.
The demand for aerial intelligence grew enormously as World War I went on. And after the war, the technology continued to improve. Custom-built cameras were created that could work at faster speeds and from greater heights.
The big difference between the end of World War I and World War II was the advent of the automatic camera. This was the F-24, which was typical of those early cameras. These would have been the best lenses available to the British at the time. Electric, motor drive, the whole thing is plugged into the aircraft electrics, and a simple switch in the cockpit gives you the ability to take 20, 30, 40, 50 frames.
As the cameras got faster, so did the reconnaissance planes that carried them. This was a necessity, as enemy fighters grew more adept at shooting them down. The British matched speed with speed. They stripped the guns and armor off a Supermarine Spitfire, one of the fastest fighters of its day, and fitted the plane with an F-24 camera. Its mission? To take secret photographs inside Germany. The idea was conceived by maverick Australian inventor and pilot Sidney Cotton.
Sidney Cotton is perhaps the single most important figure in the creation of modern photo reconnaissance technology. He was one of the few to appreciate that reconnaissance could be taken beyond the confines of the battlefield.
Just before the start of World War II, Cotton put his recon ideas to the test during business flights over pre-war Germany.
Cotton's great breakthrough was not perhaps using anything that didn't exist in the day. He used standard cameras. His concept, of course, meant that they were concealed in the aircraft. The aircraft was used clandestinely for photography.
Cotton rigged his plane with a hidden camera. His plan was to covertly photograph German military installations. What he hadn't counted on was a close encounter with the enemy that could easily have led to a death sentence.
There is a story that Sidney Cotton actually undertook one of his missions with a senior German officer on board the plane, entirely unaware of what was happening below him.
And when he switched on the green light in the cockpit that said cameras running, the general said to him, "What does that do?" And he said, "Oh, that's my fuel state." Cotton was a man with almost no nerves, clearly.
On the eve of the Second World War, Sidney Cotton had invented the spy plane. But even as Cotton was flying his covert sorties, a new technology was being tested, one that would ultimately require surveillance planes to do more than just hide their cameras. The invention was radar, and it would soon transform military aviation. By allowing ground installations to see approaching aircraft, it created a need for new and innovative tactics.
Radar is actually the first effective way of seeing without your eyes. You can actually find out where things are at considerable distances. Once you know exactly where they are, now you can talk about dealing with them.
The advent of radar made wartime aerial reconnaissance more difficult, but it served its purpose in World War II, and by war's end, Sidney Cotton's legacy, the spy plane, was only just beginning to show its full potential. It would be during the uneasy peace of the Cold War that aerial surveillance would truly come of age. The man who would write the spy plane into the history books was Clarence Kelly Johnson, then head of Lockheed's Skunk Works Advanced Development Division.
Kelly Johnson was just an unbridled genius. And you can just see in his daily journals how his mind worked and how he would take a design, a very advanced design, from the earliest stages to the final stages and always be ahead of the problem. He believed that he knew what was needed by the customer, and he would deliver it to them, sometimes even before the customer knew what they needed.
This time, his customer was the CIA, and he was developing a spy plane with the deceptive designation U-2. for utility plane. By 1950, radar was powerful enough to see 10 miles high. That was also the altitude limit for Russian interceptors. So Kelly Johnson designed a plane that would fly higher than both. The U-2 could go beyond 70,000 feet, more than 13 miles high.
The U-2 was a remarkable concept in that it was very simple. It was basically a high-flying sailplane powered by a jet engine.
The U-2's first flight was in August 1955. A year later, it began operating over the Soviet Union, giving the U.S. an unprecedented look behind the Iron Curtain.
This ability to see what the enemy is doing, to photograph what's going on in the Soviet Union so that you can actually discern on the ground what the facilities are doing, what the plants are doing, what nuclear facilities are, whether they're exploding atomic weapons. This ability, in a sense, to photograph the Earth and to see what's going on in your enemy's territories.
At last, the true breadth of the Soviet armory could be accurately documented. Flying and photographing 13 miles above the Earth, the U-2 enjoyed unobstructed access over enemy soil. But on May 1st, 1960, the U-2's cover was blown sky high. While on a secret CIA mission to photograph Soviet ICBMs, U-2 pilot Gary Powers was shot down over the city of Sverdlovsk by the blast effect from a Russian surface-to-air missile. Soviet Premier Nikita Khrushchev showed the world pieces of the destroyed airplane to prove that the Americans had been spying. Powers was put on trial and sentenced to 10 years of prison and hard labor. But 2 years later, he was repatriated in a prisoner exchange for a Russian spy. He made it home in time to witness the U-2's finest hour. In October of 1962, photographs taken by a U-2 revealed Soviet missile installations in Cuba, less than 100 miles from the Florida Keys. For 13 days, the Cuban Missile Crisis brought the world to the brink of nuclear war, until the Russians agreed to dismantle the installations. But the crisis also illustrated the importance of aerial surveillance and spy planes. The U-2 has patrolled the skies ever since and seen action in both Gulf Wars. After the Powers fiasco, however, it never again flew over the Soviet Union. But that never stopped Kelly Johnson, who was already thinking up the next incarnation of the unstoppable spy plane. He spoke about it in a 1975 interview.
We knew that, overflying Russia for 4 years, that they were making important advances in radar and missiles. And so in 1958, 2 years before Gary Powers was shot down, we decided we'd try to make a follow-on airplane, which became finally the SR-71, to fly higher and 4 times as fast.
Johnson was proposing a leap into the future. Just over a decade earlier, Chuck Yeager had broken the sound barrier. Now, Johnson set out to build a warplane that could go 3 times the speed of sound. At more than 2,000 miles per hour, no missile would be fast enough to catch it. The plane was called the SR-71 Blackbird.
If anyone had asked an ordinary designer to build an airplane with the requirements that were laid out for the SR-71 at that time, they would have said it's impossible.
The Blackbird demanded entirely new technologies. Unlike the aluminum-skinned U-2, the SR-71 was made of titanium to withstand the heat generated at supersonic speeds. Even its fuel had multiple uses. It acted as hydraulic fluid and helped cool the plane before it was burned. The Blackbird's shape was also unprecedented. The Skunk Works engineers completely redrafted the blueprint for a warplane. But by far, the biggest challenge was the engine.
The designers faced the problem of having an engine that would work all the way from takeoff at 0 speed up through Mach 3.
But there was no engine in existence that had that kind of extreme capability.
Turbojets are good at the lower speeds, but for good fuel efficiency at higher speeds, you need a ramjet, where the air flows through the engine, is burned, and then goes out with the fewest obstructions possible.
In a conventional turbojet working at subsonic speeds, compressors at the front of the engine squeeze air into a combustion chamber, where it is ignited to create thrust. But at supersonic speeds, the ramjet compresses the air automatically as it flows into the engine, eliminating the need for the compressors. Bypassing the compressor discs actually makes the engine more efficient, but the ramjet only works at high speeds.
In order to avoid putting both ramjets and turbojets separately in the same airplane and pay a big weight penalty, the genius of Pratt & Whitney was to add these bypass tubes around the core of the turbine.
At lower speeds, the conventional turbojet would provide the thrust, but at speeds over 1,600 miles per hour, the bypass tubes would divert the air directly into the afterburners, creating a ramjet that would work without the compressors.
At speeds somewhere above Mach 1.5, the engine begins to pass more and more air through these tubes and less through the core of the engine.
The engines and the rest of the SR-71 Blackbird were all created in secret. On December 22, 1964, Kelly Johnson and top Air Force brass arrived at Beale Air Force Base in California for the plane's first test flight. This would be Johnson's proudest moment. His masterpiece would soon take its place in active service alongside the U-2. Johnson had engaged the best engineers at Skunk Works, and all their reputations were on the line. Test pilot Jim Easton flew in the chase plane that day. But it wasn't long before he too had a chance to see what the Blackbird could do.
We'll just let this thing cook and we'll see where it goes.
The Blackbird didn't take long to pass Mach 2.
Gee, the next thing I know, this thing clicked up to about 2.3. I said, maybe we're on to something. Just about the time we went back over our base, 3.0 showed up.
The Blackbird took Jim Easton 3 times faster than the speed of sound, more than 2,000 miles per hour. Kelly Johnson's genius hadn't just pushed the limits, it had knocked them clear out of the sky.
No other airplane had made a similar leap forward, not from the Wright brothers on. No other airplane had become that far in advance of all others. And it was, of course, a Mach 3 airplane. It could, with in-flight refueling, it had virtually unlimited range, and it could fly anywhere, and while it might be detected, it couldn't be attacked. The surface-to-air missiles simply couldn't react swiftly enough to attack it.
Only 17 years after Chuck Yeager's historic flight in the Bell X-1, Kelly Johnson's Blackbird was cruising at 3 times that speed and outrunning missiles in active service. Other experimental craft like the X-15 have reached the hypersonic region above Mach 5. But to date, no operational warplane has ever flown faster than the SR-71. The Blackbird served for 25 years before being retired and is known to have outrun more than 4,000 missiles without a single combat casualty. But high-altitude supersonic speed wasn't feasible or appropriate for all kinds of combat. And closer to Earth, other warplanes were not having the same success as the Blackbird. In the Arab-Israeli conflict of 1973, the highly trained Israeli pilots in their American and French-made fighter planes were blindsided by the latest generation of Russian-built surface-to-air missiles, or SAMs. Israel's Air Force may have been superior in the sky, but their dominance was nullified by the threat from the ground. The destruction was devastating.
Over 19 days of conflict, the Israeli Air Force lost 109 airplanes, representing 35% of its pre-war combat aircraft strength. Quite clearly, had the war gone on for any extended length of time beyond that point, the Israeli Air Force might have been taken out of the conflict.
Ultimately, Israeli ground troops secured the victory. But her Air Force suffered a huge blow from the radar-guided missile. Back in America, the U.S. Air Force was taking notice. The destruction of so many American-made warplanes like this F-4 Phantom came as a shock. The SAMs forced the U.S. to reevaluate its fighter plane priorities.
A very imaginative response was to attack the radar system itself, and do this by reducing the radar signature, the radar cross-section of the attacking airplanes.
Air Force engineers realized that if they could make warplanes invisible to radar, no one could see them coming, and enemy missiles would not be able to lock on. It would take a while, but the result would be the F-117 stealth fighter. It's the first warplane designed from scratch to be invisible to radar. Since radar works by bouncing radio waves off an object, the key was to create a surface that deflected the waves.
Radar is a sensor that uses microwaves to detect the presence of targets within its vicinity. By transmitting a signal into the space around it, the targets reflect echo signals back to the radar and therefore give away their presence.
Imagine this flashlight as the radar source and the metal as the warplane. The light or energy bouncing back from the metal represents the reflected radar signal. The amount of energy bounced back is determined by the radar cross-section of the object.
Radar cross-section is the term used to describe the echoing area of a target. So in essence, the size of the target as perceived by the radar.
To determine the cross-section of an item, a microwave generator is used to provide radar energy. Testing different shaped objects will reveal how some present a large radar footprint, while others become practically invisible. The goal is to minimize the radar return.
Here we have a shaped target. We see that it has a rather large flat face. Now, let's put this back in with the flat face facing directly towards the radar itself and see what we get. We can see now that there's a very large target response here that is recording a signal strength here of 24 milliunits.
To avoid a radar-guided missile, a warplane signal would need to be almost zero. At Lockheed's Skunk Works Advanced Technology Division, designing planes to evade defenses was by now second nature. The U-2 had been created to fly over them, the Blackbird to outrun them, and now they hoped stealth would deceive them. Kelly Johnson wasn't convinced the technology would work, but he was no longer in charge. His hand-picked protege, Ben Rich, was now running the show.
Ben Rich was an incredible character, a one-of-a-kind guy. He took over running the Skunk Works from Kelly Johnson in 1974. To most people in this country, and particularly in the U.S. Air Force, he is viewed as the father of stealth.
Despite the doubts from his former boss, Rich decided to take the risk.
Ben Rich was going really to stake his reputation, and indeed the reputation of Lockheed and the Skunk Works on, was a stealth program.
Rich put together a team of specialists from a variety of disciplines. The first breakthrough came from the radar expert.
Dennis Overholser walked into Ben Rich's office and said, "Ben, I think I've got a layout that we can come up with that has a very, very low radar cross-section." And Ben said, "You mean down to about the size of an eagle?" And Dennis said, "Try an eagle's eye."
The key lay in the shape and alignment of the surfaces.
We can now reorientate our target to direct the apex of this pyramid directly towards the radar system. Now bear in mind, the radar still sees the same square shape of target, the same area, but the shapes of the facets and their orientations towards the radar are clearly different from the first case.
Suppose this was 1 meter square, and you held this up at right angles to a radar. The equivalent radar cross-section would be about 1,000 square meters. If you bend it back to some shallow angle, it would drop down to a number like about 1/10 of a square meter. Now if I rotate it like a diamond, clearly it's still a big mirror just like it was before, but I tip it about this angle, it now drops down to about 1,000th of a square meter. So from 1,000 to 1,000th, it changes by a factor of 1,000,000. So all you have to do is to make your airplane of a lot of diamond-shaped sections like this, and you got a very low radar cross-section airplane.
The team from Lockheed was beginning to believe radar could be fooled.
Well, it's fairly obvious that the strength of the echo has gone down enormously. And the marker readout is confirming that the amplitude, the strength of this reflection, is now a mere 4.5 milliunits.
Ben Rich and his crew now had the ability to make a plane almost disappear. The faceted shape would deflect most of the radar signal, but there was still more work to be done. They needed a special coating to absorb the small amount of radar energy that wasn't deflected. The team came up with a new coating, but it was a time-consuming solution.
What you're looking at is just the outside sheeting. Every time you do any maintenance on this aircraft, you have to strip back that coating, remove a panel, do your maintenance, put the panel back on, and then recoat this coating. Basically, you scrape this stuff off, and then you put it back on in layers. And it's not a simple brush it on and let it dry. There's several layers like a composite fiberglass. It's very tedious and repetitive work.
This outer layer brought the plane's radar cross-section down to almost nothing.
This is radar absorbent material. And what we can see here now is a flat response where we once had the echo. But for all intents and purposes now, that target has disappeared from the radar screen, and we've achieved a very stealthy performance.
Every F-117 stealth fighter has an entire department dedicated to the upkeep of its radar-absorbent skin.
We call them Martians, which stands for material handlers. They're very special folks because without them, this aircraft is just another airplane.
We have roughly about 10 people per shift come out here and work on aircraft, mostly all night long. We're the main guys of the stealth fighter. Without us, there's no point in having it.
The F-117 is a radical rethinking of the warplane's design. It's ideal for eluding radar, but its faceted shape creates problems. The plane is unstable and not at all aerodynamic.
If it wasn't for computer aircraft control systems, we would not have any chance of flying that airplane successfully.
Without a computer, the F-117 might leave the ground, but it wouldn't stay aloft for long.
With the computer in the loop, the pilot now told the computer what he wanted the airplane to do, and the computer would try and figure out how to give the pilot what he was asking of the vehicle. The one thing this allows you to do is fly things that you could not normally fly, things that are unstable. Shapes like the F-117, which would be unflyable without a flight control computer on board.
The flight control computer transforms the pilot from a technician into a tactician. Together with another electronic advance called fly-by-wire, it takes over the job of keeping the plane aloft, freeing up the pilot to focus on the mission at hand.
If you can imagine that this broomstick is an aircraft, and an unstable aircraft would be like this. I balance the broomstick on my hand, and I let go of it, and it falls over. It's very clearly unstable. So now if you can imagine, the broomstick is the aircraft, and my hand and I am the flight control computer. And by watching the broomstick, I can balance the broomstick on my hand and stabilize it, which is the same thing that the flight control computer does on the digital fly-by-wire aircraft.
The fly-by-wire part of the system is the way the messages get sent from the computer to the plane's control surfaces. Instead of mechanical cables, the system relies on electrical signals. This saves weight and maintenance and also increases stability. The first active service plane to make use of these features was the F-16 Fighting Falcon. The F-16 is a relaxed stability aircraft, meaning it's maneuverable but inherently unstable. With the flight control computer and the fly-by-wire system, however, the pilot doesn't have to worry about making constant adjustments to keep the plane aloft. The F-117 was built around this capability. Its effectiveness was showcased during a test flight when the chase plane noticed a serious problem.
The chase pilots called out and said, I think it'd be a good idea for you to return home because the left fin just fell off your airplane. And the interesting thing was that the pilot did not know that because the computer automatically compensated for the lack of the control system, and he was flying along without any knowledge of the fact that that happened to him.
Fly-by-wire and the flight control computer gave the F-117 wings. The design and coating provided stealth, but only war would put it to the test. In February of 1991, 42 F-117s flew into a maelstrom of ground fire over Baghdad. They returned without a scratch.
You see AAA fire and you see surface-to-air missiles being fired because they were firing at something that they thought they had seen on radar.
In the heat of combat, the F-117 had proven beyond all doubt that stealth worked. Secrecy had now been added to height and speed as a feasible means of defense. The next step was to scale up the technology, and the Air Force was already working on a long-range stealth bomber. Called the B-2 Spirit, its design was informed by the positives and the negatives of the high-maintenance F-117. The Spirit doesn't need an army of Martians to prep it between flights. Instead, robots and a new radar-absorbent coating ensure a quick turnaround. Its unique shape is a throwback to earlier times.
One of the advantages of a flying wing is it's a very efficient airplane because it's nothing but a wing. It has very little drag, so as a result, it has very good long-range performance.
The B-2 has a 172-foot wingspan and can fly 6,000 miles without refueling. The flying wing's low drag means it can also carry very heavy and deadly payloads. The B-2's distinctive silhouette is a modern take on an old design that was ahead of its time. The original flying wing was designed as a proof of concept. An early but still working prototype lies in a dusty hangar at the Planes of Fame Museum in Chino, California. It was built in 1942 by a man who believed streamlining was the way to maximize efficiency. His name was Jack Northrop. Instead of a tail, Northrop devised an ingenious method of steering the plane. He created a set of clamshell flaps at the back of each wing. The pilot could open and close them one at a time. When a clamshell opened, it created drag above and below that wing, making the plane turn. In 1940, Jack Northrop's first prototype took to the air. The clamshells worked. He was convinced the flying wing would be the shape of the future.
The point of it was it demonstrated that you could actually have a flying wing that did not have a rudder and a vertical tail, and yet the plane could still fly quite safely.
When the Army Air Force saw the prototype fly, they thought it might be the answer to their search for a new long-range heavy bomber. But when the YB-49, a jet-powered experimental version of the flying wing, was tested, it displayed some disturbing characteristics.
It had problems in the sense that it was neutrally stable. It had a tendency to wallow somewhat, is the best way to put it directionally, because it didn't have a tail.
Just keeping the plane on an even keel demanded much of the pilot's time and effort.
The pilot had to damp out all these uncommanded motions. As a result, his workload was increased tremendously.
A system of gyroscopes helped keep the plane stable, but the wallowing problem could not be resolved. On June 5, 1948, disaster struck. During a test flight just north of Muroc Dry Lake in California, a flying wing crashed, killing the entire crew, including pilot Glenn Edwards. Edwards Air Force Base was later named in his honor. Edwards' name lives on. But at the time, it looked like Jack Northrop's flying wing would be relegated to the scrap heap. Until, that is, fly-by-wire and the flight computer provided the instant solution to the design's control problems.
You have gyros inside the airplane that sense when the airplane moves uncommanded without the pilot commanding it to move. And it automatically, without him taking any actions, moves the control surfaces in order to kill that motion.
With the development of the flight control computer, Northrop's design was resurrected in the shape of the B-2. The flying wing also had a built-in stealth advantage.
One of the things that was noticed during the testing of the YB-49, and it was just sort of as an afterthought, was it was very hard for the radars to see the flying wings. And they actually did do a flight test where they actually deliberately flew at a radar and said, okay, tell us when you see us. And it was surprisingly close to the radar before they actually saw them. But no one was particularly interested in that, and they just filed it away.
4 decades later, the Air Force was interested. The F-117 and B-2 were the first and second generations of stealth. The F-22 Raptor is the latest. It entered service in 2005 and is the first supersonic stealth fighter. With supercruise speeds of over 1,000 miles an hour and high maneuverability, the Raptor and other top jet fighters push their pilots to the brink. Even with computers doing much of the flying, the physical limitations of the human body have become a serious concern. At places like the National Test Pilot School in the Mojave Desert, pilots learn how to push themselves and their planes. In classrooms and in the sky, their job is to make sure new aircraft perform to specifications before other pilots take flight.
The image, what's a test pilot? Test pilot in today's world is very much a professional and a very meticulous planner. On a test program of a new type, there could be the case where things could go badly and you could end up out of control. Every little detail of test flights are planned. There have been times where control has been lost. I think it's important in test pilot training to intentionally put the new pilot in that situation and then bring him back. In our school, we put a lot of emphasis on experiencing that during the education they get here. Because of that experience, I think they're better able to handle the unknown when they get out doing tests on a new airplane.
2 of the pilots in the course are about to begin a spin test. When a plane goes out of control, pilots need to follow very detailed and specific procedures to recover. And it's up to the test pilots to establish what those procedures should be. They will be writing the manual.
If you're doing out-of-control spin testing in an airplane, you have a certain amount of time before something very bad happens.
Okay, Bill, I'm going to have you go up and stand.
So getting that practical side of the training in addition to the classroom stuff is critical to success in the future.
These trainees are going to endure moments of controlled but real danger. Staying calm under pressure is one of the first lessons they learn. As the pilots put the plane through its paces, they are monitored at a telemetry center on the ground. Banks of engineers keep track of data streamed from the aircraft as it responds or fails to respond to its out-of-control state. The measurements reveal whether the machine is reacting the way it's supposed to. Spin tests are an extreme ordeal for both plane and pilot, and throughout the spin, ground control keeps a watchful eye. If the plane gets too low, they'll give the order to eject.
Okay, it seems to be pretty stable. Yes. Okay, let's recover. Stick forward.
To function effectively under such extreme pressure, pilots must know what their bodies can do. The flight computers are programmed not to exceed human tolerances. But even so, high-speed maneuvers can generate G-forces that push the pilots beyond their limits. At the U.S. Air Force Centrifuge in Dayton, Ohio, trainees learn how to prepare for extreme Gs.
Good afternoon, Casey. You're feeling well today?
Yep. Casey is an Air Force volunteer training to be a pilot. She's about to experience her own personal spin test. Typically, the limits on a modern fighter are set at 9 Gs to protect the pilot.
Anytime you have an object that is accelerating, it's going to be subject to G-force, which is the force of gravity. When you have a high-performance aircraft that's, say, pulling a high-speed turn, you're going to be upwards of 5 to 9 times the gravity. Follow my finger, don't move your head. As you increase in G level, your blood is getting pulled out of your head and will pool down into your legs. So if you were to just sit there and do nothing around 3.5 or 4 G after about 5 to 10 seconds, you would likely lose consciousness. Okay, Casey, as a reminder, you're going to need to do the anti-G straining maneuver at 4 G and above to maintain the blood flow to your brain and prevent G-induced loss of consciousness. The first component of the straining maneuver is going to be a whole body muscle flex, and the straining maneuver should look something like this. So you want to have that nice short, sharp air exchange every 3 seconds.
Before entering the centrifuge, Casey dons her G-suit, a standard piece of equipment for all fighter pilots.
This is the G-suit, and when I get in there, they hook this up. When it gets to certain G levels, it will flow air in here at different amounts, so that there's a different amount of pressure depending on how high of a G you're at, so that you don't have to do as much straining just with your own muscles. It kind of feels like there's somebody squeezing your legs and your abdomen.
The G-suit fits tightly around her torso and legs. It will constrict the bottom half of her body to keep her blood supply in her upper body and brain. This gives her the ability to withstand 5 or 6 Gs. Once in the centrifuge, she keeps her finger on the stop button, just in case.
You guys ready?
Hey, Phil.
I feel fine.
You all set?
Yeah.
Casey's heart rate is carefully monitored as the centrifuge begins to spin.
Okay, if you're ready, we'll head on up to 5. Okay, you're at 5.
Casey begins the straining maneuver, tensing her body to stay conscious. Her breaths get sharper and shorter.
Okay, you're at 6.
When you get close to blacking out, your eyes kind of bug out. That's your body's response. And my eyes were pretty huge, so. And I can say I was very close to blacking out. I couldn't see very much, and I was thinking about pushing the stop button, but I wanted to see if I could make it through, so.
Okay, you're on your way back down.
Human performance is clearly the limiting factor in our modern high-performance aircraft. And people still lose consciousness from G exposure, despite these interventions.
The G suits and breathing techniques help, but there is only so much they can do. Pilots, despite their training and preparation, can sometimes hold their aircraft back, especially now that onboard computers can handle the flying on their own.
12:40, 1 o'clock takeoff.
You guys got any questions for me?
Nope. Okay. Great, thank you.
Thank you.
Some say fighter pilots are a dying breed.
Yeah, as I say, if you want to just...
When you look at flying in the kind of places that are so heavily defended, the pilot becomes really a premium, certainly something that we don't want to waste or lose. And so those areas that we can do more effectively by taking the pilot out of the cockpit become what us technologists seek to work on.
Their replacements are the latest generation of UAVs, or unmanned aerial vehicles. They're a far cry from your backyard model airplane. This Global Hawk weighs more than 25,000 pounds when fully loaded, cruises at 60,000 feet, and can stay aloft for 30 hours at a time.
Well, it's a little embarrassing to be the chief test pilot on an unmanned airplane for a fighter pilot. Most people think of UAVs as being airplanes with wingspans about as long as your arms, But Global Hawk has a 116-foot wingspan. So these are not toys.
They're not toys, but because UAVs don't need cockpits or safety features for pilots, they can be small, light, and flexible. Just like the first manned warplanes from a century ago, their initial missions were reconnaissance and target spotting. They were well suited for this role. In Desert Storm, Iraqi soldiers actually surrendered to an unarmed UAV by waving white flags above their heads. Perhaps it was a sign of changing times. Some UAVs are remote controlled, but Global Hawk flies without a human hand. Its powerful computer, satellite uplink, and global positioning system tell it exactly where it is and where it needs to go. Once its mission is set, Global Hawk flies alone.
Global Hawk is purely an autonomous airplane. The pilot takes his mouse, selects takeoff, and activate. Once that happens, the airplane will fly unassisted all the way to Australia and land.
Australia or anywhere else on the planet. Operators on the ground work in shifts to monitor each mission, but their work is a far cry from actually flying into combat.
We have Air Force pilots that get up in the morning, eat breakfast with their wife, kiss them goodbye, go to work, fly 8 hours of combat over Iraq, and then come home and play with the kids in the afternoon.
Not surprisingly, government agencies around the world are rushing to develop UAVs of every shape and size. They can be autonomous, stealthy, and armed. They may even fly in swarms or as wingmen to manned fighters. Equipped with Hellfire missiles, This Predator is a UAV that can turn from spy plane into hunter-killer in the blink of an eye. Here at the U.S. Air Force Research Lab in Dayton, Ohio, scientists are working on another innovative UAV. They're attempting to use fly-by-wire and an autonomous flight computer to operate and control an unstable craft that really shouldn't fly. It's similar in concept to the pogo fighter of the 1950s, which flew but was hard to control. The developers are hoping that just like Northrop's Flying Wing, their unstable craft will benefit from new technology. The vehicle is called Skytote.
Skytote is an unmanned air vehicle that flies both like a helicopter and like an aircraft. A lot of helicopters are limited in their top speed. Most airplanes cannot stop in midair. So we've found a middle ground here. So it can hover, it can have precision landing capability, yet it can also fly at a relatively fast forward speed.
This hybrid autonomous UAV could be made big enough to carry large loads or even human passengers.
What you may need to do is fly around like an airplane so you can look at a lot of area, stop, hover, and look at one area in particular in more detail. Or maybe if you have a pilot down or somebody in trouble somewhere, they need to get out in a hurry, we would be able to use this concept to go in and pick them up, again, precise landing because of the hover capability, and then bring them out. Helicopters do the job right now, but those are manned helicopters, and that puts a lot of people at risk.
There is little doubt that UAVs are here to stay, and their roles will expand as their capabilities increase. But not everyone is ready to write off the piloted warplane. Sweden, a small but high-tech country, still embraces the notion of manned warplanes and has developed its very own unique frontline fighter. It's called the Saab Gripen. The Gripen is designed to be low maintenance and highly flexible. It can be outfitted almost anywhere by a small crew and can turn most straight roads into a landing strip. Designed to carry a variety of ordnance that will meet different tactical needs, it's light, fast, and maneuverable. A ground crew of 5 non-specialized soldiers and a technician can rearm and refuel the Gripen in 10 minutes. The rapid turnaround time gives it excellent combat effectiveness, since a warplane on the ground wins no wars. The Gripen is just one example of the versatility of the warplane. Its singular approach satisfies a specific need. Throughout the world, manned and unmanned aircraft will continue to patrol the fine line between the sudden demands of war and the never-ending quest for peace. This is the role the warplane has played for the last 100 years. The biplane spotters of World War I have become today's unmanned aerial vehicles. Fighters have gone supersonic. And heavy bombers have evolved into stealthy flying wings. Again and again, technology has reshaped the warplane, which has in turn transformed the way countries wage war. There can be little doubt this pattern will continue into the future, bringing new generations of flying machines with ever more spectacular capabilities.
For more information about the 100 years of military aviation history, please visit pbs.org. A multimedia timeline will reveal how warplane technology has transformed the way countries wage war. Warplane is available on DVD for $24.99 plus shipping To order, call 1-800-336-1917 or write to the address on your screen.